Okay, you may continue, please. Can you hear me? Hello?
Can you? Okay, sir.
Yeah, Mr. DMO, you can start.
Good afternoon, everyone. Today we'll be going through error analysis, and under error analysis, we'll be considering floating point approximation of a number, loss of significance, error propagation, and stability in numerical computation. First and foremost, we need to understand what our numerical analysis is about. Numerical analysis is a branch of mathematics that studies the method and algorithm we use while solving different problems. And while solving these problems, we discover that there might be some variations in the values being used, and which may prevent us from arriving at an exact answer, or probably the algorithm being used. Along the line, we see where different errors are coming from. So we have number presentation in computer. We all know what is called standard from the scientific notation, where we say let a real number k be denoted where m is any real number raised to power times 10 raised to power n. N can either be negative or positive. We all know how this goes. If your number is a whole number, then your n will be positive. Meanwhile, if it's a decimal or a fraction, then your n tends to be negative. We can see examples of this scientific notation, the likes of 0.000000834, and when it is to be denoted in scientific form, we have 8.3 times 10 raised to power minus 6, and the other two examples that are there. Then we'll move to what is called floating point numbers. Our floating point numbers refer to either positive or negative decimal. Now, when we have these numbers, we have some numbers that you just have a number, a significant number after the decimal point, while some you have other significant numbers after the decimal point. So we can have it in a general form of a equals to plus or minus 0.d1, d2, d3, so you get to dk plus 1, then times 10 raised to power n. Our d1 can be less than or equals to 1, or less than or equals to 9. And our di also, that is the value for I, can be less than or equals to 0, less than or equals to 1. For each I equals to 2, that spans from 2 to k. We call n an exponent, and n can either be positive or negative, and can be 0 as well, as we all know that any number raised to power 0 is equals to 1. Now, when we're dealing with computation in computers, we use finite number of digits in representing number, as is denoted also in general.
Excuse me, you said any number raised to power 0 equals what?
Any number raised to power 0 is equals to 1, sir.
Is that correct?
Yes, sir.
So when you multiply 0 by a number, what does it give you?
Sorry, sir, I said raised to power 0, not multiply by 0, sir.
That's the rationale. When you say 2 raised to power 2, that's 2 times 2.
Yes, sir.
So I think the answer is infinity, not 1.
Okay, sir. Thank you very much, sir.
Yeah, you can continue.
So, like he has just told us, n number raised to power 0 is equal to infinity. And this can be represented in general form, since we said we use finite numbers in computer computations, as b equals to plus or minus 0.d1, d2, d3, dk, and times 10 raised to the power n, where 1 is less than or equals to d1, less than or equals to 9, and 0 is less than or equals to d1, d high rather, sorry, less than or equals to 9, for each I that spans from 2 to k. I'll say these numbers are called k-digit decimal machine numbers. That leads us to our main discussion, which is error analysis. We all know that as humans, we are all prone to errors. Also, we would not forget that our system, the computer system, is garbage in, garbage out. Whatever you give to it is what it gives to you back. And if we humans are prone to errors, whatever error we program or we enter into this system, the same error is recycled back to us. The same error is recycled back to us, and this might lead to differences in the solution we are expected to get. Please, can you hear me? Hello?
Yes, we can hear you.
Yeah, we can still hear you.
Yes, clearly.
Thank you. Now, what error analysis?
Somebody's hands is raised. Your Deji Alabi.
Yes, sir. So I just quickly checked Google for anything raised to power 0. The answer is 1. It's any number divided by 0 that is to infinity.
Oh, okay. That's noted. All right. The presenter is correct in his presentation. So that means if you have 2 raised power 0 is equals to 1.
Yes, sir.
Yes, sir.
Right. All right. Thank you.
Mr. Ayodeji, thank you, sir. So the essence of this error analysis is numerical analysts, they want to look at, okay, what are the possible ways by which we can minimize this error? Since we all know that, oh, it is unavoidable. But we want to look for a way to minimize it such that the answer we're expected to get will not be completely different, or will not be the difference between the answer we get and the answer we're expected to get will not be by wide margin. So, and in numerical analysis, we approximate exact solutions of problems using different numerical methods. And in the course of the approximation, when you have a number that after the decimal point you have about 16 digits, and you are reducing it to 4 significant digits after the decimal point, then you are going to cut off some numbers, and that is going to lead to some variance in the answer you're supposed to get. So now we are going to look at different errors. We have the likes of numerical error, we have approximation error, and we have relative error as well. Now, we are looking at numerical error denoted by E. So let X be the exact solution of the underlying problem, and X star its approximate solution. Then our error denoted by E, and our error denoted by E is given by E equals to the absolute value of X minus X star, the absolute value of the exact solution minus the approximate solution. Now, we are going to look at sources of errors in numerical computation. We have the gross errors, we have the modeling or formulation error, we have the data uncertainty error, and we have the discretization error. Now, the blunder or gross error, these are errors caused by human mistakes due to oversight, And this can be taken care of by doing scientific investigations. Because if we pay more attention to what we are doing, I think these errors can be reduced, since we all said they cannot be totally eradicated. Now, the modeling errors, these ones arise when scientists ignore certain factors in the model to simplify the problem. We also look at data uncertainty when the data being used or the problem being addressed has to do with physical data, and the cost of gathering it, there might be variations and then leading to some differences in the answers. And we also have the discretization error. This is computer represents a function of continuous variable by a number of discrete values. And scientists also tend to approximate and replace complex continuous problems by discrete ones, and this results in discretization errors. Now we are moving to absolute and relative errors. I mentioned earlier that the numerical error depicted by E or denoted by E is equal to the exact solution minus the approximate solution. The absolute error here, as you can see in the formula here, is given by E equals to our E equals to absolute value of X, the exact solution, minus the approximate solution. The relative error is the absolute error divided by the exact solution, by the absolute exact solution. The relative error is denoted by D, and it is equal to the absolute error denoted divided by our exact solution. Then that leads us to percentage error. All we need to do for percentage error is to multiply our relative error by 100. And this gives us the percentage error. Now let's take our text example. We have X equals to 3.141592653589793. That's the value of the constant ratio pi. Now we are asked to correct to 15 decimal places, and we're given our approximate solution to be 3.141592653. We are asked to compute the error, the absolute error, and the relative error. I mentioned earlier that for us to get the error, you subtract the approximate solution from your exact solution. That is X minus X star. Now this is the solution here. The error is given by E equals to X minus X star. And if you are with your calculator and you do this subtraction, we are going to have an answer that spans, that continues. And if you are using all these scientific calculators, there is a limit to which the screen can take, and it's going to show you that, oh, that's an exponential, the value still remains, and it denotes it by E. Now, at the point where we consider the absolute error, we did the absolute value of the X, the exact solution minus the approximate solution, as we can see here, and we have the relative error as well, and we can also see the value of our relative error. Then we'll move to round off and truncation errors. Now we all know that the elementary mathematics we learned in secondary school or primary school, as the case may be, says, okay, when you have a number from 0 to 4, you round them down to 0. And when you have a number from 5 to 9, you round them up to 1. And then add it to the value of the number close to them. That's after the decimal point, or even if it's not a decimal number. Now, these round off error and truncation errors, we're told here that computer represent numbers in finite numbers of digits, and hence some quantities cannot be represented exactly. So these errors are caused by replacing a number A by its closest machine number, and this is called the round-off error, and the process is called correct rounding. Now we have what is called truncation error as well, or chopping errors. And these errors occur when we chop an infinite number and replace an infinite number and we replace it by a finite one, or by a truncated series after finite number of times. Sorry. Okay, we have example. And I have to round off these numbers or even chop them off using the truncation rules. Here is the questions we are posed with, and here are our solutions. If we go by our elementary mathematics, or we just used two decimal places. We used 2 decimal digits for our solution. Now, if you look at it, we have for x1, we have x equals to 1.34579. Now, if you round, don't forget I told us earlier that number from 0 to 4, you round them down to 0, and number from 5 to 9, you round them up to 1. If you round this 9 up here, if you round it up, this becomes 1. If you add it to this, it becomes 8. If you round this 8 up, and it becomes 1, you add it to this, it becomes 6. And by the time you round up this 6 up, it becomes 1. You add it to 4, this becomes 5. And that's why we have for our x1, x equals to 1.35. Same thing applies for our x2. By the time we round off this 9, 7, and 6, it becomes 1. Or to save ourselves the stress, we can just come from here and round this up. By the time we round this up, this becomes, since these numbers are all greater than 5, and if we round them up, we know they are going to give us 1. So if we round this up, this becomes 1. We add this to this. It also gives us the x2 we have here, which is 1.35. Now, looking at the chopping of, I believe you all understand the rounding of part, the basic elementary part. Now, the chopping of, we also used serial numbers, 2 decimal places rather. For the questions we have 1.34579. When it comes to the chopping or the truncation, we just look at, okay, this is the decimal digit I want to use. There is no rounding off. Just once you get to the decimal position you need, just cut the others off. Now, for our x1, we have 1.34579. If we are going to go by chopping or truncation, since I mentioned earlier that we are going for 2 decimal places. From here, if we round this off, this becomes 1.35. Our S2, by the time we round this off, this becomes 1.34 as well. By the time we chop off, not round off. By the time we chop this place also, we are going to have 1.34. When we come to X4, going by our chopping rules and 2 decimal places, this becomes 3.34, and this also becomes 2.35. And that is how we arrive at these solutions we have here. Then we come to what is called loss of significance. Now, in the place of relative error, we often use the concept of significant digits. Now, loss of significance occurs when 2 nearly equal numbers are subtracted to produce a result. Much smaller numbers are subtracted to produce a result much smaller than either of the original number. The first is that the number of accurate significant digits may be reduced unacceptably. So, we want to consider examples of that loss of significance. So, we have P to be equals to, we have P to be equals to 0.54617, and our Q to be 0.54601. If we look closely, we see that the difference between them is quite small. Now, we have to use 4-digit arithmetic to approximate P minus Q, and we should determine the absolute and relative error. Then we have P and Q, reducing P and Q to the 4-digit arithmetic we have to use, and that is to get the approximate value of P and Q. Don't forget the value of P is 0.54617, now Q is 0.54601. So using the 4-digit arithmetic, this for our P, which is the approximate value of P, we have 0.5462, and the approximate value of Q is 0.5460. To get our absolute error, don't forget that we have to subtract the approximate solution from the exact solution. And to evaluate P minus Q, we have to find the absolute value of P minus Q, which is what is done here. And we have the value for our exact solution. And in this case, the question we are posed with is P minus Q, which means initially we have to subtract this from this, so that we'll be able to get the exact solution of subtracting Q from P. Then after getting...
Hello. Yeah,
yes, sir.
I feel that you could show that on the slide. So instead of jumping the steps, you have to do P star minus P, then Q star minus Q, you got a value. Then you now say P minus Q, right? And that's what led you to get the relative error.
Yes, sir.
So I think that step was skipped somewhere here where your cursor is.
You mean yes, sir?
Yes, I think there should be a step before jumping to P minus Q. Or go back a little, one slide back a bit.
Okay.
Okay, so if this is this, determine the absolute and the relative error. Now you are given that P, I think I can see, can you raise it up a bit? Okay, yeah. P equals this, Q equals this, right? Next slide.
This is the next slide, sir.
So you have P and Q to 4 digits is this. So that's the approximation. Then absolute error is, did you calculate absolute error for Q and absolute error for P?
So I did, sir, but the first thing I did was to do the exact solution, which is the P minus Q, which I was asked to do in the first place. Then I followed for the absolute error of P minus the exact solution, that is the exact solution minus the approximate solution, rather, of P star and Q star, which is for P, this is it, and for Q, this is it, sir.
Oh, okay. I think I've seen it now. That's what I was looking for. Okay, all right, sir. All right. You are correct.
Thank you, sir.
Because I thought you just subtracted straight up without doing P minus P star, then Q minus Q star data. The steps are clear.
Okay, sir. So we have the exact solution, which is P minus Q, which is here. Then we have the approximate, the error for subtracting the approximate value of P from the exact value of P. So which, if you've done that on your own calculator, you have 0.0003. And for Q, by the time you subtract your Q star from your Q, you have 0.0001. That takes us to our approximate solution for P minus Q. We're just calling the approximate solution for P minus Q. Now, after we've done our P minus Q, the question we asked to, the subtraction we asked to do in the first place, which is we got 0.0016. And after we're able to get our error, the P star and our Q star, the difference when we after we subtracted P star from P star from P star from P and Q star from Q, we got 0.003 minus 0.0001. This is for P star, P minus P star, and this is for Q minus Q star. So we need to perform the same operation of P star minus Q star to know to have our concluding answer, which is this. Now, by the time we subtract that, we subtract 0.0001 from 0.0003, we get this answer. Now, our absolute error, which we are asked to compute using a 4-digit arithmetic, is given by the exact solution of P minus Q minus the approximate solution of P star minus Q star, which is what we have here. By the time you do this calculation, you are going to get your absolute error for 0.0014. Then we'll move to what is called relative error. And we should not forget our relative.
Hello.
Yes, sir.
Yeah, where you have A, that's absolute error for P minus Q. Now, the formula that you have just reiterated wasn't supplied there. Or where you, no, wait, no, not where your cursor is. A, absolute error.
Okay, sir.
Where you wrote A, put your cursor on A. Yes,
Okay, sir.
there. So you have absolute error for P minus Q from using the 4-digit arithmetic is given by that. Now, the formula you used to arrive at that has not been given. I'm sure, I think I heard you say P star minus Q star or so.
Yes, sir. Okay, sir. Sorry, sir. Are we?
No, you can, I'm just reminding you so that just make a mental note of it so that once you are doing your correction for the slide, that
Okay,
can
sir.
be well situated.
Okay, sir.
Then the last group that submitted their slides. Now there was a slide, of course, I was looking at, I don't know, maybe it's Taylor series, but I saw Tyler or something. I'm not sure if that is correct. So please visit it and redo it and resubmit. There was a lot of errors in that submission. All right. You may continue.
Thank you very much. Thank you very much, sir. Now, don't forget that the formula for our relative error is absolute error over the exact solution. Now, on getting there, our absolute error, which is 0.00014, then we need to, don't forget we got our exact solution earlier. From this point, exact solution for P minus Q, we got 0.00016. So that's where this exact solution we use is coming from. So we just substituted for our absolute error, which is 0.00014 divided by 0.00016. And if you do that with your calculator, this is the answer you're going to get. So this gives us the absolute error here, and it also gives us our relative error, which we have to solve for in the question we are given. We move to error propagation. Sorry, please excuse me. Don't forget we said, I mentioned something earlier that our computer system goes by the garbage in, garbage out. What you give to it, it recycles back to you. Now, that leads us to once an error is committed, it affects subsequent results as this error goes through or continues through the subsequent calculations. Now, if the approximate values of two numbers x and y are x prime and y prime respectively, then the absolute error is given by just the same, what's it called, that we are recalling here, that the exact solution x minus the approximate solution s prime. And for y, the exact solution minus the approximate solution. Now we have different mathematical operations which we go by. We have the addition, we have the basics actually. We have the addition, we have the subtraction, we have the multiplication and division. Now for the addition, the absolute error in addition operation is given by the exact solution x plus y to be equals to our approximate solution plus the error, the absolute error of our x, which is denoted by E subscript AX or EA. And also we have that for y. Because we are adding this together, that's how we arrive at this x prime plus y plus y prime plus x plus EAY rather. Now, by the time we collect like terms, opening these our brackets here, this gives us s prime plus y prime plus the error, the absolute error of x and the absolute error of y. And if you see the same collecting like terms, I will go by here. And this gives us x plus y minus x prime plus y prime to be equal to the absolute error of x plus the absolute error of y. Now, the other side of the equation is showing that the absolute error of x plus absolute error of y should be less than or equal to when you find the absolute error of x alone plus the absolute error of y. If we have done our calculation well, if, take for example, let's assume the absolute error of x is 2. Take for example, the absolute error of x is 2 and the absolute error of, it should be y, sorry. The absolute error of y is 3. By the time we had it together, we are supposed to have 5. And if we are doing it separately also, when they are having their own absolute value separately, that is 2 here and plus, what's it called, 3 here. That should be, this, what is here should be less than or equals to the answer we're going to get here, which if we have 2 plus 3, we're definitely going to get 5. And if you have 2 plus 3 also, we are definitely going to get 5. That's why you have the less than or equals to symbol. Then we'll continue with our error propagation. We go to the subtraction. Now, the subtraction, if it goes almost, addition and subtraction, they follow almost the same procedure, except for the operations carried out on them. And what do I mean by the operations? In the place when you are adding, for subtraction, you are reducing. When you are increasing in addition, you are reducing in subtraction. Now, that the same formula we have for x minus y equals to x prime plus EAX minus the y prime, which is the approximate solution, plus the absolute error of y. Now, when we open this bracket, we know that this bracket will multiply everything within this bracket. This minus will open this bracket. So that's why we have minus times y prime. This gives us minus y plus minus EAX as EAY rather, as we have it here. Now, by the time we collect like times like we did earlier, this x prime minus y prime crosses over to meet the x minus y, which is the exact solution in the first place, which will lead us to the absolute error of x minus the absolute error of y, which we are expecting that it will be less than or equal to the absolute error of x and the absolute error of y.
Hello.
Yes, sir.
Yeah, I think there's a consistency in your use of absolute error of ax and another ax. So I think that should be changed as well to y. So that, and I think in the previous page, I saw something in that regards to.
Yes, sir.
So please look at it when you are doing your final correction.
No problem, sir. Thank you, sir. So, and we discovered that here we have absolute value of x minus the absolute value of y. We're expecting that it should be less than or equal to absolute value of x plus the absolute value of y. And you'll be wondering, we have what we call the minus here, and here we have plus. Because of this, our absolute value, we know that even if our answer is negative, with the absolute value symbol, it's going to change to positive, which is why we said because of the mode here, this negative changes to positive. We also have our absolute error in product of numbers. So take for, sorry. Okay. Now for multiplication, we say let EA be the absolute error in the product of two numbers x and y. So write x plus, our approximate solution is EAX plus x into bracket y plus EAX minus xy. By the time we will continue the process of solving, we have EAX, reason because of opening the bracket. We have EA to be equal to x EAY plus y EAY plus EAX EAY. And EAX EAY is negligible because it is very, very small. Now we have the formula for the absolute error in division are depicted by this. Then we move to what is called stability in numerical computation. What is numerical stability? Stability in numerical computation refers to the ability of a numerical algorithm or method to produce accurate and reliable results, even in the presence of small perturbations or errors in the input data or intermediate calculations. Now, when we are dealing with stability in numerical computation, there are three main aspects of stability in numerical computation. We have the algorithmic stability and the numerical stability. One that deals with the algorithm and one that deals with the numerical value being used. So the algorithmic stability refers to the inherent stability of the
sorry, just a minute. Now, I think the essence of going through this kind of class or a course is for you to understand that some of the things you'll be getting coming across as you journey through the field of computer science, there are these little bits of things, and they will become very pronounced in research, right? You are talking about stability. Oftentimes, when people do researches and they do performance evaluation, they present some figures, they present some numbers. Now, the question we always ask is that the error level that you have reported, because we don't expect you to get 100%. So the question we now ask is that if you have a percentage amount of error or a percentage of error, does that error really affect the whole solution? For instance, if you have a live, maybe in the hospital, if somebody is on life support, now we expect that the error that is permitted in that kind of situation should be zero. Why do we say zero? We will not say, okay, let us just be thinking that NEPA will not strike, will not take light. We will not expect that somebody cannot be so careless as to unplug the oxygen machine or breath supporting machine. We cannot be so careless to say that, okay, we should not have another source, even 3 sources of power supply, because what we are looking at that period is life critical. And if there's a little bit of error, as much as 0.001, that person may die. However, we could have error that are permissible in some areas of research. For instance, you are doing something on classification, you are doing something on segmentation, you are doing maybe some performance evaluation on some complexity of algorithms. Now, those that are not life dependent or life threatening can have a percentage error. However, we want to look at what is that percentage error to the effect on the working of the system. Now, in his lecture, he started that some errors just come just because of approximation. Some error comes because of truncation. Some error comes because of a number of other issues. Then he went further to tell us about how errors are propagated. Now, some errors, if committed now, by the time you go through, for instance, those of you who are going to be doing things on AI, you have why maybe a neuron will fire or a neuron will not fire. When we say fire, that means it's able to transit from one level to the other. It's able to produce results when inputs are supplied to it. That's what we call fire. So if you have an error from the initial state, and that error keeps propagating, maybe forward feedback or backward feedback, and it continues, you find out that as soon as you multiply one error by the next, it appears to increase. When you add another layer of error, it continues to increase. Now, it can increase to the point that it will threaten the research that you have conducted. So you may feel that, oh, what is the essence of doing all these courses and all that? This is the crust of research in computer science. And if you don't understand it, you would have done a lot of good research. And by the time you do the performance evaluation and you present the results, you will find out that what you have done so fantastic becomes a nightmare to you. Right now, I think myself and one other student in Lund University in Sweden, we just concluded the research. And while we were working, we were trying to make sure that the errors that we are getting is not propagated into the next phase of the research. Because as you are interpreting the first results and you propagate the error into the next one, you find out that the efficacy of your result becomes watery, right? And it continues to just mess up the research you are doing. Now, there are some research area in computing that has to do with evaluating innovation, right? There are a number of systems that have been developed that have become very useless now. There are some apps that are just there online that are so useless. However, when they were produced, it was a piece of innovation. But when evaluation was carried out on it, on the effect for which it was, the innovation was brought, we found out that its interaction is almost zero. For instance, we have three main languages in Nigeria, right? We have Yoruba, Hausa, and Igbo. Now, you now take, for instance, you have your ATM. You now take it to the village in maybe Onu in one state in the east. You bring another one maybe to Zungeri in the north. You bring another one to Lajwe in southwest. Now, if you have brought an innovation called ATM, is it not still better for you to install the language or things that people can relate with on that machine? Instead of say, enter your PIN number. Somebody that doesn't understand English, how does he want to enter it? So we found out that though ATM is an innovation, but by the time when you carry out performance evaluation on it based on location, it has failed that test. And that's why you feel that penetration of accounts, e-account or something, is failing. Because you tell me to bring my money, you come to my village, you speak Yoruba to me. When I get to the bank to go and withdraw, you now start speaking useless English that I don't understand. The next time, I will not bring my money to your bank. And again, that innovation will not be adopted and the penetration will not be successful. So by the time you are doing penetration testing on ATM, you find out that just because of the error in language. Now, you can see, he also mentioned that errors can be analog and can be discrete, right? Errors can be continuous. That means physical quantities that you can see. Then the physical quantities that you see that is analog can also be sampled and converted to discrete structures. That's why you call sampling error. Now, if those errors are tested, the ATM is tested based on location, of course, it will fly in VI, it will fly in Unilag, it will fly in some other places, but can ATM fly in the village? That's why you don't have banks in the village. And money exists so much in the village, especially those cocoa farmers, those petrol people in the villages, they have money, but they prefer to keep cash because ATM as an innovation has failed penetration testing, has failed user testing. And if you look at the percentage, the error will be so high that it will even outwit the usefulness. That means the usefulness of ATM in deep villages, the error is high. So that technology will be dropped. And as you have seen, except you have not gone to your village or you don't have a village, you can't find ATM in those villages. So innovation that is meant for everybody, as a matter of fact, has been reduced to an elitist innovation. Coming back to this class, why are these things important that you are learning? It is all these small things that translate into those big grammars that you see in papers that you read, that you see in textbooks that you read. Little things. So you need to have a bit of an idea of all these little bits. I'm sure, of course, some people who are not who have not started with computing, as you may not even understand what analog systems are. You may not understand what discrete systems are. How can you convert analog signals to digital signals? So you must have this little bit of understanding before you can be said to be a computer scientist. You are not just writing programs. Okay, if you write programs, maybe as a non-computer scientist, what about the complexity of the algorithms? How do you calculate it? What is the significance of complexity of algorithms? What kind of strategies do you use? What kind of search strategies do you use? What kind of solution do you apply in solving the problems you have written a nice code on? So there's a possibility that you can have your head in the air and you don't know anything. Whereas what is hitting you up is really, really down there. And these are the pointers. These little things are going to be helping you even in your final year projects, because you're going to do performance evaluation of a developed system that you have done. You're going to be doing proof of concept in what you have developed and a lot of other things. So you have to minimize error as much as possible. So if you feel that, oh, this is just mathematics, no. That's why we didn't send you to maths to go and learn it. Mathematics will just teach you theory of computation, theory of whatever. But here, we want to teach you the theory, which is the science, and also the possible application area. So at the end of this whole course, you're going to have an assignment where you're going to implement some of these algorithms that you are mentioning as you go by. So I just want to quickly point it to you so that you don't say, what is all this? But, you know, the lecturer, the presenter has constantly moved from one level to the other, and telling you and maybe showing you, okay, when you move from this kind of error exists, this kind of error exists. So now is at a stage where it's telling you that though error exists, how can we stabilize it that it doesn't affect our results? So please pay close attention, because in your journey in computer science, you're going to be looking at a lot of algorithms, right? And some mathematics. But I feel you should pay more attention to the algorithm side, because you may do courses on complexity of algorithm, development of algorithm, and that is the crust of computer science. You're going to be doing theory of computation, computability, and a host of other things. So don't see all those big mathematical notations there. See the application area in computing. So the presenter may continue as the class goes on.
Thank you very much, sir. So we go back to algorithmic stability. So we say this refers to the inherent stability of the mathematical algorithm used to solve a particular problem. We'll continue to say an algorithm is considered algorithmically stable if small changes in the input data lead to only small changes in the output. And this ensures that the algorithm does not amplify errors or produce significantly different results due to minor variations in the input. And numerical stability refers to numerical stability now. Numerical stability refers to the stability of the algorithm when implemented on a computer using finite precision arithmetic. We mentioned earlier that computer represents numbers with a finite number of digits, leading to the introduction of rounding errors during calculation. Numerical stability is concerned with how these errors propagate through the computation and affect the final result. A numerically stable algorithm minimizes the accumulation and propagation of these errors, producing accurate results even in the presence of limited precision arithmetic. Now, numerical analysis deals with developing methods called numerical methods to approximate a solution to a given mathematical problem. And that is when a solution exists for that mathematical problem. Because if the solution does not exist, there is no point looking for the approximate solution or to reduce any error. The approximate solution, like we treated earlier, obtained by this numerical method will involve an error, which is precisely the difference between the exact solution and the approximate solution. So the exact solution is given by approximate solution plus the error. And we call this error a mathematical error. Now, the outcome of the computer code is a set of numerical values to the approximate solution obtained using a numerical method. Such a set of numerical values is called a numerical solution to the given mathematical problem. During the process of computation, the computer introduces a new error called the arithmetic error, given as an approximate solution equals to numerical solution plus arithmetic error. Don't forget we said exact solution is equals to approximate solution plus error. But during the computation, when the system is performing its own, it pops up another error called arithmetic error. Now telling us that our approximate solution is equals to numerical solution plus our arithmetic error. Now the error involved in the numerical solution when compared to the exact solution can be worse than the mathematical error and is now given by, okay, our exact solution is now equal to our numerical solution plus mathematical error plus arithmetic error. That is the error here, which is also known as mathematical error. And don't forget our approximate solution is equal to numerical solution plus arithmetic solution. By the time you substitute the value, what our approximate solution is equal to, into this particular equation, we have our exact solution to be equal to numerical solution plus the arithmetic error. This error here, which is also known as mathematical error, which is why we have this our exact solution to be equal to numerical solution plus mathematical solution plus arithmetic error. Now, the total error we encounter is defined as a mathematical error plus arithmetic error. Okay. Now, the stability tells us what is possible or what we can expect when solving a continuous problem with discrete arithmetic. It also tells us what it means to get the right answer, even if it is not the exact answer. An abstract way to think of solving a problem is like evaluating a function y equals to f of x, where x represents the input to the problem, and f represents the problem itself, and y represents its solution. An algorithm can be viewed as a different function f prime that usually takes the same data, actually the rounded data, and maps it to the different function f of x, f prime of x rather. For example, the computer code used to implement the algorithm is viewed as the f prime, like we mentioned earlier. So if two different implementations are meant to produce the same result, rather, these are generally two different functions, f prime of f prime subscript 1 and f prime 2. Then we have this, if nothing else, f prime will be affected by rounding errors during its execution. If f prime is a good algorithm, we might expect the relative error to be small, e.g., some small multiple of units round off. And we say that f is an accurate algorithm for f prime is an accurate algorithm for f if for all the relevant input data of x, we have absolute value of f.
Excuse me. So did you just call that f prime? The f prime you're calling it?
You mean
sign, yes. Yes.
Yes, I meant f prime of x.
Okay.
Thank you. F prime of x minus f of x over the problem post itself, which is f of the absolute value of f of x, will be equal to 0 underscore subscript u subscript e, where our o is the unit rounded off. And we continue further. We say a number of mathematical problems have solutions that are quite sensitive to small computational errors. For example, rounding errors. To deal with this phenomenon, we introduce the concept of stability and condition number. The condition number of a problem will be closely related to the maximum accuracy that can be attained in the solution when using finite length numbers and computer arithmetic. This concept will then be extended to the numerical methods that are used to calculate the solution. Generally, we will want to use numerical methods that have no greater sensitivity to small errors than was true of the original mathematical problem. Don't forget, we mentioned that, and like our lecturer mentioned to us, that in some computation, when the error continues, it tends to increase. So we, in this process of stability and condition number, we are looking at a solution that attains maximum accuracy and that helps us to reduce and the errors, and that means it does not have great sensitivity to small errors when we are doing our computation. Now, to simplify the presentation, the discussion is limited to problems that have the form of an equation, f of x comma y to be equals to 0. Our variable is x, the unknown, being short, and the variable y is the data on which the solution depends. These equations may represent many different kinds of problems. For example, f may be a real value function of the real variable x, and y may be a vector of coefficients present in the definition of f. Or the second one, the equation may be an integral differential equation with x an unknown function and y a given function or given boundary values.
Sorry, excuse me, I have a question. Your
Okay.
previous, that's I think number 25. Okay, that f prime of x, is that a differential of f of x?
If you follow from the
How did you get the f prime of x? F prime of x?
if you follow from the 24th slide, said an algorithm can be said as a different function f prime. So that's where the f prime of x is coming from. I usually take the same data and map it to a different solution, f prime of x. So we are saying f prime of x is a solution to the initial problem, which is x.
Okay, thank you.
Are you okay? Now, the equation may be an integral differential equation with x an unknown and function y a given function or given boundary values. Now we say that the f of x equals 0 is a stable solution if the solution x depends in a continuous way on the variable y. This means that if y of n is a sequence of values approaching y in some sense, then the associated solution values xn must also approach x, in some way. We're saying if we say the solution of x depends continuously on y, as y of n, which happens to be a sequence of values, is approaching y, then the x of n also must be approaching x in some way. And equivalently, if we make even smaller changes in y, this must lead to correspondingly smaller changes in x. If there is a little variation in x, or in little variation in y, it should lead to a little variation in x. And if there is a greater variation in y, it should lead to a greater variation in x, which is telling us that the equation is stable. That is, the effect the variation has on y is the same effect is having on x. Meanwhile, if it's inverse, that is, if the change, either small or great, in y does not, if it has a small change on y and is having a greater change on x, then it means our equation is not stable. Or if the change is small on y, then the effect on x is great, then we say it is not stable. Now, the sense in which the changes are small will depend on the norm being used to measure the size of the vectors x and y. There are many possible choices varying with the problem. Now, stable problems are also called well-posed problems. And if a problem is not stable, it's called unstable or ill-posed. And with this, I come to the end of my presentation. Thank you for your time and thank you for So listening.
All right. Thank you for your presentation. I don't know. Do we have questions for the presenter? Questions for the presenter? Well, I think the presenter has done the best as lies within his power. Now, I think you see, this is one of the effects of coming late to the class. And I think the class rep came late to the class the first day of the class. And I asked that the grouping should be based on those who were in class that day, right? So, you know, a number of PGD students have dropped out of the program, or some of them will not be taking this course. Now, you have grouped some people in groups that they will not even show up. Now, I think there are about 4 or 5 in their group, that's group 5, and only one person is available to do a bit of presentation that he could go about. Now, this seems so unfair. Now, if those who attend classes promptly, about 20 of you, were shared into the group, so you at least you have about 3, 3, 3, 3, and 2 in the last group. So in a way, it helps individual, right? So what about in another session, nobody in that group, everybody in that group has dropped out. So that's why I said those in class should be the ones that will be in the group, but the class rep in his own wisdom just shared everybody, probably those offering and those who are not offering, right? So that's what is affecting maybe the output of the presenter. Notwithstanding, I will send in lecture notes on this topic, at least just to be a support system for the individual who has tried all his best to go for the materials and also presenting as gently as he can. And of course, I want to believe that we have gained 1 or 2 things during his presentation. So I don't know. Have you prepared your questions? Do you have anybody's hands raised up? All right. Nobody. All right. Can we send in our names for attendance quickly? Attendance. Yes. For the group that presented last week, please can you send your details on the chat group, not here, but on the WhatsApp group, your name, so that we'll be able to record your scores and start taking in the records. Now, I'm sure you are bearing witness now that the last group, how many of you were in the last group, please? Huh? No, I mean on the original list.
4, sir.
4, that means one person decided not to join the presentation. So by default, I assume that person has dropped out or is not taking this course. Now, today, the presenter, how many of you were in the group initially?
4, sir. 4, sir.
4. So we have just one person presented. So we have 4 people who will not have CA as it stands, right? So by the time they start jumping up and down that maybe it's one devil that was chasing them and they didn't have to, maybe they didn't have the opportunity to do tests and all that, I feel that this record will be to their, at least will be to their discredit, because people are fond of wanting to, they want to gain where they did not sow. Now, this individual who they have subjected to a lot of stress, mental stress,